Now we'll look at the second problem from that free response, and this one has a lot of symbols. The algebra can get a little bit tricky, but most of this problem actually doesn't have to do with rotational dynamics. Most of it is force diagram review. So a key thing to note, it gives you a bunch of symbols that you should work with, but a key thing to note is that the two blocks on the table move relative to each other. So you cannot group these two into a single 7m system because they don't have the same acceleration. They slide with respect to each other. So to find the vertical tension with the symbols that are given, you just need to draw the force diagram for that vertical mass because that's the only place that the vertical tension will show up. So force diagram for this one, pretty simple. 2mg is the weight, and using the symbols that they tell us to use, TV would be the upwards tension. So accelerating down, I would say 2mg minus TV is equal to 2m times A. So TV would be equal to 2m times g minus A. For the horizontal tension, I'm going to focus on the 3m because I know that that horizontal tension will act directly on that mass through contact. So if I draw the force diagram for the 3m block down here, I would have horizontal tension force. It says there is friction between blocks B and C, but the table, I think it is frictionless. Block C, surface coefficient. That's horizontal surface, sorry. So there is no friction on the 3m mass by the table. There is the 4m sitting on top of it, so there is a normal force, Fn, on the 3 by the 4, but I know that this is equal to the weight of that force, so I'm just going to go ahead and write that this force is going to be equal to 4mg. We have the weight of this block, that's 3mg. We have the normal force on this thing by the table that you can see is going to be equal to 7mg because this mass only accelerates to the right. And then if I think about this 4m mass on top, that thing's going to be accelerated to the right because of a frictional force between the 3m and the 4m. So the force on this block is to the right on that 4m block, so that means that the force of friction on the 3m by the 4m has to be to the left. So now I can write my net force equation. That's going to be equal to 3m times A, and that force will be TH minus FFK. That's equal to 3m times A. Now I'll be able to do some substitution to finish this thing off. So using our kinetic friction model, coefficient times normal force is equal to the force of friction. Coefficient is an allowed symbol in here because they give it to us there. So I can say that the horizontal tension force is going to be equal to 3ma plus coefficient of friction times 7mg, because this normal force is what matters for frictional force. No, it doesn't. Hold on a second. This is not the right normal force. That would be between the block and the table. So this should be the normal force that's responsible for the friction force, which is between the 3m and the 4m. So this is the correct normal force to go in there. So try that again. The horizontal tension force would be equal to 3ma plus mu times 4mg. Okay, the next step is where we start to think about rotational dynamics, free body diagram for the pulley wheel. would look like this. There's the pulley wheel. We got to draw forces at the point of application. So it doesn't really matter where I put these, but I'm going to put them kind of where the string comes off from it. We have the horizontal tension that's trying to cause a counterclockwise rotation, the vertical tension trying to cause clockwise rotation. TV is clearly larger than TH because we know that the pulley angularly accelerates clockwise. To be complete, we should also include a gravitational force and a normal force from the axle on this thing, which, given the way I drew my horizontal and vertical tensions, it would probably have to go some way in this direction. But since I'm going to have my torques go around this center axis, those two forces, Fg and Fn, are not going to contribute to my net torque equation anyways, because they're operating at a radius of 0. So now for an angular expression of the angular acceleration of the pulley wheel, I'm just going to start with net torque equals I times alpha. Now I in this problem, the moment of inertia of the pulley wheel is given. So I'm just going to go ahead and make that substitution first. That's 3 capital M radius of the pulley wheel squared. The acceleration of the hanging mass is going to be equal to the angular acceleration times the radius of the pulley wheel. Because that string is connected up here, it doesn't slip. So the way this thing angularly accelerates is going to be linked to the way this thing linearly accelerates. So I'm going to go ahead and make this substitution here and put this as A over R of the pulley wheel. Oh, I'm sorry, back up. I don't need to find that linear acceleration, so I could just leave this as alpha. Then thinking about the torque, I just have TV acting at this radius R minus TH acting at that radius, same radius R. So TV R minus TH times R. So now solving for alpha, TV times R minus TH times R over 3M R squared. The squared can get rid of those, and so we have our simplified expression, TV minus TH all over 3M R. TV and TH are allowed in this expression, so I don't have to go any further than this. In part E, your test had 2 meters per second squared. It's giving you the linear acceleration, and it says find the coefficient of friction. Well, all the work you've done so far has kind of set you up for this. You have an expression for TV, you have an expression for TH, you have this expression. We know that alpha is equal to A over R. So now we just need to substitute in all these expressions that we have. So TV is equal to 2M times G minus A. TH is 3MA plus mu times 4mg. And then alpha is up there, this expression here. So we have 2mg minus 2ma minus 3ma minus mu times 4mg. All of this divided by 3mr is equal to A over R. Now we can cross off a bunch of stuff. M is in every term, so those cancel. And we have R over here. If we multiply both sides by R, that goes away. And then I'm going to work with G equals to 10 so that I don't have to get out my calculator. So 2G is 20 minus 2A. A is equal to 2, so that's minus 4. 3 times A, that's 3 times 2, so minus 6. Minus 4 times G, that's 40 times mu. That's equal to A, which is equal to 2. So we have 20 minus 10. Bring this over. That would be minus 2 more. So 8 is equal to mu times 40. So mu is equal to 8/40, which is 0.2. And then for the acceleration of the block, block C. Block C is the one that's sitting on top. C has a mass of 4m. So the force diagram for this would look like this. 4mg, normal force equal to 4mg, and a forward directed force, which is this force of kinetic friction, which is equal to the coefficient times the normal force. So mu times 4mg is equal to the net force, which is equal to 4ma. So mu times g, so 0.2 times 10 is the acceleration of block C, which is 2 meters per second squared. So now that I get to the end here, there's something up with this acceleration, because this is the same acceleration that we said the 3m block would have, but if the 4m block and the 3m block have the same acceleration, then there would be no slipping at the surface. So this wouldn't be kinetic friction that we're talking about. This would be static friction. But I'm not quite sure why that ends up being this way. So if you find a mistake in here, that would be great.